couple of years ago, I made this. What I thought was a simple experiment ended up becoming one of my most popular projects. But despite how complete it looked, it never really worked like it's supposed to. So today I'm rebuilding it properly with 6 degrees of freedom, better ergonomics, better software support, and a design that you can still build yourself. At the end, we're going to compare it to the real SpaceMouse and see how close it actually gets. Let's get started. This video is sponsored by Brilliant. More on them later. So what was actually wrong with the first version? The problem was that I built something that looked far more complete than it really was. Mechanically, it was convincing, but with just a single magnetic sensor, I was missing a huge part of the motion data needed for proper 6-axis control. So a lot of the navigation had to be stitched together with mouse and keyboard emulation, which kinda worked, but it was clunky, inconsistent, and never really felt like the real thing. That became a lot more obvious once I'd spent some time with an actual SpaceMouse from 3D Connection. After using one properly, I had a much better sense of what this device needed to do, and where my first version was falling short. Full disclosure, this one was sent to me through the Autodesk Creator program, but no money exchanged hand, and this is definitely not a review. The other thing that I wasn't fully happy with was the size. The knob was too tall and too bulky, and while the mechanism worked, some of the moving parts inside were more complicated than they need to be. So for this project to be a success, it needed to accomplish 3 things. Deliver full 6 degrees of freedom control, have better ergonomics, and work reliably within the software. With those goals in mind, the first place to start was the internal mechanism. I changed the spring platform to a simple 3D printed flexure that I could iterate on and fine-tune much more easily. I made this parametric file in Fusion and tested a bunch of versions to find the best balance of thickness, geometry, and feel. The important detail here is the material. I used PETG because it gives a more consistent deflection and a better fit for something that needs to flex repeatedly. The stem is fixed to the base, the flexure sits on top of it, and the control knob mounts directly to the spring itself. This will make more sense once the rest of the assembly comes together. In the previous version, I used this off-the-shelf module from Adafruit, which meant I can only read 3 axes, so this time the idea was to use 3 sensors arranged in a triangle around the stem, giving me 9 readings to work with and hopefully enough information to derive the 6 degrees of freedom reliably. Of course, using 3 modules would have been way too bulky, so to validate the idea I ordered just the sensors IC from DigiKey along with some adapters to prototype with. I also made the 3D printed jig to hold everything in place temporarily. After soldering a whole bunch of wires, I added the stem and the flexure from before along with this holder to keep the magnets hovering over each sensor. While I was looking through the Infineon Arduino library, I found an example using 3 sensors at the same time, and that's when I noticed the problem. These sensors don't have a hardware way to set different I2C addresses, so if you put them all on the same bus, they all appear as the same device. The example seemed to be bringing them one by one during startup to assign addresses in software. So I added these little power switches using the same kind of dip adapters so I could control power for each sensor separately. I then wired the rest of the prototype on the breadboard with 2 simple momentary switches and a Jow RP2040 as the main controller. After struggling with the initialization code for a while, I finally had readings coming from all 3 sensors at the same time. But as you can probably notice, they all have completely different values on every axis. What I actually care about here isn't the raw readings, it's the change that happened when the flexure moves. So the first thing I did was grab a set of readings on boot and use those as offsets to bring everything closer to 0 and make the output a lot easier to read. That helped, but there is still some jitter around the neutral position, so I added dead zones like before to ignore small unwanted movement, along with some filtering to smooth the signals out a bit. For translation, it was pretty much the same as before, except now I had 3 times the readings, so I simply averaged them to estimate motion in X, Y, and Z. Rotation was a little less obvious. For the pitch and roll, I used differences in the Z-axis reading to estimate tilt from left to right and back to front. And that seemed to be working well enough. The last one was trickier, but because I knew where each sensor sat around the center of the triangle, I could combine each position with its readings for X and Y to estimate how much the knob was twisting around the middle. So with all the 6 values mostly there, I added gains to control how much each one contributes, along with the way to invert the direction if needed. I then tied everything into a 3D demo over serial so I could control the camera and see how it actually feels before going any further. At this point, I had motion data that was starting to look usable, but that still didn't mean that the computer would know what to do with it. Most input devices communicate with the host through something called the HID protocol. Without getting too lost in the weeds here, when a device enumerates, it provides a sort of a template called a report descriptor. That tells the host what kind of device it is and what format the data should expect to receive. That data then gets passed to the driver to process and relay to the applications. So to see what that looked like on a real SpaceMouse, I used this tool to dump the report descriptor and run it through a parser, which made it a lot easier to see what was actually going on. There was a bunch of vendor-specific stuff in there that I really didn't care about, so I simplified things down just to the parts that I was interested in: the device type, the 6 axes, and the 2 buttons. Once I had that descriptor, I could start sending reports whenever there was movement or button presses. So now the data was in the right format, which was great, but that was really only half the battle. The other half was driver support, and here where things get a bit dicey. The only alternative driver I could find was this cool open source project called SpaceNav, which works as a drop-in replacement but only on Linux and FreeBSD. I was able to get it running and tried out few example programs. If you're on macOS or Windows though, there is another way to make the native 3D connection driver pick up this device. That's by having the firmware pretend to be an existing supported product. And look, I'm not going to tell you what to do or not to do here, but for obvious reasons, the project files I'm sharing won't include these values in them. But for demo purposes though, here's what happens when I compile the firmware with those values in place. The driver immediately thinks this is an older wired SpaceMouse compact, giving you access to the complete integration stack in any software you would actually want to use this device with. I tried it in Fusion 360, Onshape, Blender, KiCad, and even Bambu Studio, and it was working surprisingly well across all of them. It still needed some tuning to really dial it in, but for a prototype this was already good enough to move on to the next step. To make this more permanent and easier to reproduce, I needed to get rid of the mess of wires and clean up everything properly. So I designed this simple board with the sensors in the right positions and added the 2 side buttons from the prototype and few LEDs around the stem as indicators. You'll also notice I left the controller off this board, and that was mainly for 2 reasons. First, the sensor board will sit fairly high in the enclosure, so having the USB cable come out straight off the same PCB would have made things a bit awkward. So instead, I broke everything out through these headers to a small adapter board that holds the controller separately. The other reason is it makes it a lot more modular. If you want to try another controller or make a wireless version, for example, you just need to swap the adapter board instead of redoing the entire thing. And I know, this is the part where the project can start to feel a lot less approachable. So along with the files, if you want to order and build your own, I'm also sending a small batch of assembled boards to production in a couple of weeks for anyone who doesn't want to deal with sourcing parts and soldering tiny components themselves. You can pick one for yourself from the link below. With the board design done, I sent the first test order to friends over at PCBWay and moved on to redesigning the final enclosure. I already had the spring and magnets holder from the prototype, so the knob fits around those, which lets the whole assembly be a lot more compact than the previous version. One set of screws go through all the 3 parts and pull everything together. From there I used the knob assembly along with the sensor board as references to design the base around it. It's very similar to the previous design. I added the diffuser, the outer shell, and 2 side buttons positioned so they can get captured between the shell and the PCB. That all gets covered by the hollow base, to which we'll add some weight later like before. Keeping the controller separate also lets me place it lower and closer to the bottom so the cable can come out at a more appropriate height, with this little cover holding it in place. All the screws go in from the bottom, and I made sure to use only M3 hardware this time. Aside from the spring, which I had already printed in PETG from the prototype, the only other part that wasn't regular PLA was the diffuser, which I printed in a translucent filament to spread the light more evenly. The parts came out pretty decent straight off the printer. I only added the heated insert to get everything ready for assembly. Like last time, I also added these steel BBs to the hollow base to get as much weight into it as possible and stop the device from sliding around while using it. One thing that was a bit annoying on the last version was the rattling, so I mixed up a little bit of 2-part silicone I had lying around and carefully poured it in to seep in between the BBs, fill the gaps and bind them in place, with the added bonus of the little extra weight. This is definitely not necessary, but it's a nice extra to have. With the enclosure ready, the only thing left before final assembly was the electronics. The board itself is pretty simple and the soldering is fairly straightforward. There's nothing especially tiny or difficult here, but since not all the parts have leads you can solder easily to, I'd recommend sticking to solder paste with a hot plate or hot air for all the SMD parts. A few bridges needed a bit of cleanup after reflow, but nothing too complicated. And like I mentioned before, if you don't want to deal with any of this, you can skip this part by picking one pre-assembled from the link down below. I also soldered the headers with the boards in place, which made lining everything up a lot easier. For the final assembly, I ended up switching the outer shell and the knob to resin prints with epoxy inserts to get a better surface finish. You can still do this in FDM if you want, and if you're up for a bit of extra finishing, you can follow pretty much the same process as in the previous version to improve the look. Putting it together is actually pretty simple now. We start by fixing the spring to the stem through the spacer like on the prototype. That drops into the knob, followed by the magnet holder, and then all those get pulled together with 3 M3 screws. Next, the 2 6x3 neodymium magnets get pressed into each opening. They should only friction fit or stick to the screw, there is no glue needed here. For the base, the diffuser goes in first, followed by 2 small buttons and the sensor board. That all gets secured with 4 screws through the weighted base. The knob assembly mounts with 3 screws from the bottom, and the controller just plugs in the little space and gets closed with the small lid and 2 M3 screws. And that was basically it. After flashing the latest firmware, it was finally ready. With the final version assembled, it was finally time to put it side by side with the real SpaceMouse. Physically, I think something in between the first version and the real device makes a lot more sense. The knob is much more compact than my first one. The range of motion is also surprisingly close. It's still not identical, but it's very close. And the stiffness is easy to tune by just modifying the PEG spring. I didn't bother adding hard motion stops. If the springs deforms permanently, it's cheap and easy enough to replace. At the moment there are 3 states. On startup, it runs a calibration to offset the sensor readings, which is indicated with the blue light swirl. Once the LEDs turn green, it's idle and ready to send movement in button presses. After a little while of inactivity, it goes to sleep where the LEDs turn off and the knob becomes unresponsive. To wake it back up, you just press one of the buttons, or if needed, hold both of them few seconds to run calibration again. But the most important test was always going to be how it felt in the actual software. So here it is side by side in CAD, doing the exact same movement as the real SpaceMouse. And for the most part, I think it held up really well. The only thing that still falls a bit short is how the signals are meshed together. Because I'm calculating the axes separately, they tend to bleed into each other a little more than I would like, especially on rotation around the X and Y where I use that simple tilt estimate from the Z axis. This part can still be improved a lot in software. From what I understand, what it really needs is proper sensor calibration and some kind of pull solver algorithm so all the motion gets computed together instead of axis by axis. Getting all that modeled properly in a way that cancels out the unwanted translation is still a bit above my head right now. But even with that, it's still way better than the first version. I personally like tackling projects like this hands-on. A lot of the learning just comes from iterating through problems and slowly building intuition for parts I didn't really understand before. And that's what I also love about today's sponsor, Brilliant. I've been using it for a couple of years now, and it's one of my favorite ways to learn new things. Brilliant helps you build skills in math and coding through interactive step-by-step lessons and personalized practice. So you actually work through concepts bit by bit instead of just watching someone explain them. So whether you want to explore data analysis, strengthen your math fundamentals, or learn coding in Python, you can build those skills at your own pace by actually using them. It's designed for pretty much anyone, whether you're 10 or 110. After finishing this project, I started their course on coordinate transformation, and honestly, I think a better understanding of this topic would be really helpful for improving the motion processing in the current version. To learn for free on Brilliant for a full 30 days, go to brilliant.org/Salim, scan the QR code on screen, or click the link in the description. Brilliant's also giving my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. All the files and resources are linked below as usual, and the build guide will follow in a couple of days. If you have any ideas, suggestions, or possible improvements, let me know in the comments below. I hope you enjoyed following along, and I'd love to hear what you want to see next. Thanks to Brilliant for sponsoring the video, and thank you for watching. I will see you in the next one.